Welcome. I hope everybody had an easy time getting on to our session today. We're going to get it kicked off right now. The session, Learn about IBM Quantum's Scalable Hardware and Software and Build Your First Quantum Game. And I'd like to introduce to you at this time Anamita Guha, one of our speakers, and James Weaver, our other speaker. And I will let them introduce themselves as we get into the session. I will, all of you are muted now, I believe, but I'm going to unmute you and now if you could all go on mute yourself, then we can go ahead and get started. This way you can interact with the users by muting and unmuting yourself as we go through the session. Put you back on mute, but feel free to unmute yourself as we get going. And with that, I am going to turn it over to Anamita to kick off the session. Anamita, I'm going to make you a presenter. And you should be good.
Nice. Thank you very much, Neil. Just need to figure out how to share my screen. All right, did it work?
Can see it.
Okay, great. So hello, everyone. Thank you for joining us. I don't know if this is your first Think session or you've been following along with the programming all day, but if you are new to IBM, welcome. If you're new to quantum computing, welcome. My name's Anamita Guha. I work on the product team at IBM Quantum, and today I'm really excited to partner with my colleague Jim, and together we're going to take you through some high-level descriptions about what is quantum and help you get started, and then do a hands-on coding session. And hopefully by the end of this, you guys can say, hey, I can speak intelligently about quantum, and I built my first application on a quantum computer. So that being said, let's get started. I would like to note that anything we show or present to you at the slide or this presentation is subject to change and typical liability steps. If you guys want to take a second to look through this slide, then we can get started. Okay. With that, I'd love for you guys to meet Jim, who will be my partner in crime for the next 2 hours.
Hi. Well, this is James Weaver. Thank you very much, Anamita. My friends call me Jim. Please do. I'm lucky to be a colleague and a quantum developer advocate, and with IBM Quantum, and I've written several books, mostly on Java and classical computing, but the latest one is on Raspberry Pi, and I would like to actually maybe do a quantum computing with Qiskit book at some point.
Okay, thank you. And just a little hello about me. I work on the quantum team in the product management side. I have a background in AI. I went to school at Berkeley. I like post-it notes and color coding my thoughts. In a previous life, I was a yoga teacher, and I am an ambassador with the AAAS, which is the American Association for the Advancement of Science, focused on getting women and girls into STEM careers. All right. I'm not sure how I can see answers to this, but we wanted to kind of gauge the audience today to figure out how detailed or undetailed we will get going into the slides. So I'm going to ask a series of questions, and I will, maybe if you guys want to respond into the chat, and sent to all. So the first question is, how many of you are new to programming? Could you
Actually, Anamita, there is on their panelist area, there is a check mark or a raise hand that they can do so that you can see it in the panelist area.
Okay, great.
Okay, or in the participant area.
Found their hand raised. Can you get to click it to test it so I can see what the hand raise looks like on my end? I see. Cool. Perfect. Okay. So the first question is, how many of you are new to programming? Please raise your hand. Thank you. Second question is, how many of you are new to Python? A couple of you there. Great. And then how many of you are new to Qiskit? A lot more of you here. Okay. How many of you are new to quantum computing as a whole? Cool. So, Jim, I'm sure you looked at those answers. So I think about half of us are new, and then the other half are presumably quantum experts. If you feel like you're a quantum expert, please raise your hand. Cool. Okay. So thank you for bearing with me through that exercise. I'm excited to welcome you all from all these different levels, and hopefully we will all walk away with feeling like we've learned something. So the first slide that I have shown here, does anyone recognize this picture? Maybe we use the hand raise function again. Do some hand raises. So can anyone guess which year this is from? I'm going to rattle off some years and maybe you raise your hand to that. Do you think this is from the 2000s? 1980s? 1960s? 1950s? 1940s? 1930s? So this picture is from the 1940s. It's the first electric programmable computer, and it's the Colossus Mark II. I like to show this picture in most presentations because it's kind of where we are today with quantum computing as a whole. So we have a long way to go, and we're going to get very far, but if we're thinking about where we are as an industry and a space and where we are with quantum computers, we're kind of like the 1940s. Does anyone know the quote? Richard Feynman? Keep raising hands. So Richard Feynman is a physicist that he's very, very, very involved in quantum physics and very motivated to see this field move forward. He has this famous quote where he says, "Nature isn't classical, damn it. And if you want to make a simulation of nature, then you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." And Richard Feynman was a proponent of quantum computers because it's the way to actually simulate nature. We've been working on this research for a long time. So this is a picture of the Endicott House in 1981, which is where a lot of individuals in the quantum computing field got together and discussed the future and science and collaborated and brought us to where we are today. So as we get started, we'll go deeper into the code, but I wanted to spend some time to do some high-level thoughts and just talk through about where the industry is as a whole. So when we talk about quantum computing, one of the most basic things that we think through are what are the fundamentals and how is it different from a classical computer. And the most basic thing that you should know, and if you were to walk away knowing the difference between a quantum computer and a classical computer, is that a quantum computer runs on qubits. How many people have heard the term qubit before? Cool. So a qubit is not the same thing as a bit in the sense that it is it's two states at once. So a classical bit is a 0 and a 1, and a qubit is 0 and 1 at the same time. So let me visualize this for you. Think of this as a coin. A bit is heads or tails. A qubit is while it's spinning at the same time, you can kind of think of it to be heads and tails. So if you realize that it's living at two states at once, and that's kind of how you visualize it. The thing that makes quantum computers unique is that qubits can be entangled, and that's the second property of a quantum computer. Entanglement is when two qubits are together, which means if one qubit is a 0, then the other one will also be a 0. If one qubit is a 1, then the other qubit will also be a 1. There won't be a state where one's 0 and the other one is a 1. So to show this, we can look at two coins. You can see that they're both realized to be 0 and 1, even though they're in a superposition, or a qubit state. So entangled qubits are important because this is what gives quantum computers their exponential power. And you can kind of see two qubits can have the same power as effectively 512 bits. And as we continue to grow the qubits that we have in our quantum computers, the power and representation in a regular classical computer is a lot more. And the third property of quantum computers are waves and interference. So as a qubit goes through, or as a wave pulse goes through a quantum computer, they all add to each other to give out these reads of 0s and 1s. So three properties of quantum computer: qubits, which superposition, it can be 0s and 1s, entanglement, and interference. This is what a quantum computer looks like. We call this the chandelier because it looks kind of like a pretty chandelier. And the way it works is you're working from a classical computer that's encoding different gates, which you'll spend a lot of time on today. It takes an input and it goes through the quantum computer. Inside here is where the qubits are, and that will send out a pulse, which then sends out a different readout and gets re-encoded as a 0 and 1. The reason why I'm showing this 2 to the n passes, if it's a 50 qubit device, that means it can take 2 to the 50 to pass through this device. So a way to visualize the exponential power. So what can we do with quantum computers? A quantum computer is never going to be used to like something on Facebook. Quantum computers are specialized computers that are going to be the most efficient and effective if we're using it for specific applications that are hard for quantum computers. And those sorts of problems are in applications of chemistry, material science, machine learning, optimization, things that have a lot of data and a lot of input, but a simple output. That's where we're going to see a lot of efficient use of quantum computing. So with quantum computers, we're able to tackle problems in new ways, and it could be looking at physical processes of nature, finding better patterns in AI and machine learning, doing better optimization solutions, as well as performing more significant scenario simulations. And we can also build games, new games, and we'll go into that today, and you guys will also build your own game. And the way that we're all going to be able to do this is because we have quantum computers available for your use on the cloud. So for most of history, for you to access a quantum computer, you had to build it and you had to maintain it yourself. And the only way you'd be able to do it is if you had access to an academic research lab, and it looked something like this. But just over 4 years ago, that changed, and IBM put quantum computers on the cloud that everyone can access and which you will learn how to access today. And since launch, we have over 200,000 registered users on our platform that are using it, over 140 billion circuits in total run, and 400 million run on a typical day, and we have 15 quantum systems on the cloud for you to use. And we've thought about how quantum computing can be effective to different types of users. So for individuals that want to go and build their own circuits and get started with the hardware, we have the IBM Quantum Experience. For individuals that are developers and want to get more involved in the code, we have Qiskit. And for clients and universities that want to partner with us to create papers and find joint research, we have the Q Network. So today we'll be spending some time with Qiskit and IBM Quantum Experience, and Jim will get us into more details with that. But before I leave, I want to share of the 105 partners we have. We're partnering with all sorts of organizations, and you can see these are a simulation of where different experiments and circuits are being run across the world. At this instance, in 4 years, we've had quantum simulations run from all 7 continents, including a researcher in Antarctica that used our systems to run some simulations. So here are some examples of different industry partners, different hubs with universities, different clients and members of our network, as well as startups and academic organizations. So if this is something of interest to you, feel free to reach out to me or talk to me separately. But I would love to pass over now to Jim that will take us to our hands-on coding section.
Jim?
Yes, thank you very much. And you're able to see me now? And I would like to share my screen. Have I been given permission to share my screen, Neil? Very good. Please verify that you can see my screen, please, Anamita or Neil.
Yep.
Okay, great. All right. So welcome to this session. Thanks, Anamita, for the run up and for the great education on the state of quantum computing and the history. And I'd like to continue then on that track. But first, I'd like to show you where the home page is for the presentation and the resources. It's at a place called Qiskit, Qisk.it, here at the top of the screen, /think2020. And this page has all the resources that we're going to walk through today, including our slides. Here's a resource. It's a game that I'm going to show you. This session, there's game in the title, so I'm going to actually use a game to help you get up to speed on quantum computing. There's links to our quantum computing frameworks and the IBM Quantum Experience, as well as to the lab that you'll be going through today. So this first link here, my presentation slides, if I click that link, I'll get to these presentation slides. And since Anamita did such a great job in introducing you to the subject and history, I'm going to start several slides into this one so that I can pick up what Anamita talked about as far as exponential growth. And this idea of every quantum bit that you add, you double the size of the state space. And so you can tackle exponentially large problems with each qubit that you add. For example, Anamita talked about this idea that Dr. Feynman challenged us about, which is to simulate nature. We can't, right now, we can't really do a good job of simulating nature past about 40 or 50 quantum particles, or 40 or 50, let's say, electron orbital systems. And that is because every time you add a quantum particle, you double the size of the state space. And with a classical computer, you run out of memory after about 40 or 50. And that's because every quantum particle that you're trying to model, let's say that if you were trying to model 1, it will take 2 complex numbers to do that. If you try to model 2, it takes 4 complex numbers. If you try to model 3, it takes 8 complex numbers. And so you see where this is going. If I had 10, it would take 1,024 complex numbers. And we get to where we kind of break over into what you can't hold classically when you get to around 53 qubits, which is what we've got in our 53 qubit system. And we're continuing to improve upon that. As Anamita said, when you get to about 300 qubits, so we're trying to, let's say, model a 300 electron orbital system, you would need more quantum or more states than there are observable atoms in the universe. And so that's why you can't do some things. You'll never be able to do some particular things classically, but we hope to be able to do them quantumly. By the way, if you have questions during my part of the presentation, please raise your hand, and then Neil will be looking for that, and will then ask me, or go ahead and allow you to ask that question. So one of the things that got us excited about quantum computing was in 1994 when Dr. Peter Shor published an algorithm called Shor's algorithm, and it has the promise of breaking RSA encryption. One of the steps in RSA encryption, to be able to break it, is to factor a very large number into 2 prime numbers. And he found an algorithm that can run on a quantum computer that will do that exponentially faster. And then the following year, Dr. Love Grover published an algorithm called Grover's algorithm, which does searches quadratically faster. So it would take if you had a million records in unsorted records, let's say, then classically you would have to go through all of those records. You would have to do 1 million hits to be able to satisfy yourself that it's either there or not there. But with Dr. Grover's algorithm, you can do that in 1,000 queries, which is the square root of 1 million. So it's quadratically faster. Some of the near-term quantum computing domains that are kind of a sweet spot for where we're at in the near term are machine learning, as Anamita mentioned, chemistry, as she also mentioned. There's this area of optimization, being able to optimize paths, or any kind of problems, even like financials, where you're trying to optimize portfolios. Those are all things that are the near term very good for quantum computing. But it's not like classical computers are going to go away. We'll always need, in my opinion, classical computers, high performance computers, to do things that are in the wheelhouse of classical computing. But when we need to do something that a classical computer can't do, like model a chemical compound, and things like that in high dimensional spaces. Then we could think of the quantum computer as a quantum processing unit that we then request the services of to do that very computationally complex thing that's in the wheelhouse of a quantum computer. So I want to give you a little bit of an introduction into quantum mechanics. I'm going to show you some resources here real quick that you can then take a look at later at your leisure. One is this idea of being able to observe quantum mechanical effects through an experiment, through polarized light filters that you have in your sunglasses, or that you can purchase for $1, you know, from a science site. Here's a video by 3 Blue 1 Brown that talks about that you can look at later. And the idea is essentially that if you have a couple of light filters or 3 light filters and they're polarized, depending upon the way that you position them, either 100% of the photons, which are quantum particles, will pass, or 0%. But here, where we've got them at 90 degrees, where 0% of the photons will pass, then we can interpose one that is 45 degrees, and actually, by adding a filter, more light will get through. As a matter of fact, 25% of the photons will pass through. And we can directly observe through that experiment quantum computing or quantum mechanical properties. So here's another video that explains that. And then here's a great resource that one of our colleagues, Brian Ingmanson, created for workshops like this, especially geared toward kids, where they can go through this experiment. Now what I'd like to do is talk about the axioms of quantum mechanics, some pretty heady stuff for a Tuesday afternoon. And instead of using Schrodinger's cat, which was either live or dead, I'm going to talk about grumpy cat, which is either grumpy or happy. And so I'm going to tell you a fictitious story. I've got this microscopic cat, and he's often grumpy, but sometimes he's actually happy. But you know, I've never seen him anywhere in between those two states. And so that brings me to the first principle, and that is the superposition principle. My cat can be in any combination of grumpy and happy. So if I've got a unit circle here, so the unit circle meaning from the origin to the edge of the circle here is 1, a length of 1. I can represent in this 2-dimensional space, I can represent a grumpy cat over here by putting a dot right here, a 1 on the grumpy axis, and I can say in vector notation here that my grumpy cat is 1 on the grumpy axis and 0 on the happy axis. Let's say I have a happy cat. I can represent that cat in this 2-dimensional vector space as 0 on the grumpy axis and 1 on the happy axis. Now that's all classical, right? Those are bits. But I can have a superpositional cat. I can have a cat in my quantum world before I've ever observed him. And that cat can be in some superposition or some, if you're familiar with algebra, just some linear combination of grumpy and happy. This would be the coefficient of grumpiness, this square root of 1/3. This would be the coefficient of happiness, the root of 2/3. So I can represent my cat in the quantum world, quantum mechanically, with the root of 1/3 grumpy here and the root of 2/3 happy. I can also represent them in this notation that Dr. Paul Dirac invented years ago for being able to, that physicists like to use, where I can put those coefficients or those amplitudes, as physicists say, in front of this cat here, inside of this notation called a ket. And so I can say root of 1/3 grumpy plus the root of 2/3 happy. The reason I say plus is because here we've gone plus on the grumpy axis, and here we've gone plus on the happy axis. If it were down here, it would be root of 1/3 grumpy minus the root of 2/3 happy. Again, if you have questions, please let me know. Well, you've done quite well. You've gone through the first axiom of quantum mechanics. The second one is called unitary evolution. And that's where my cat can evolve from, let's say, a grumpy state into a happy state. And so we'll go ahead and apply a NOT gate or an X gate to my grumpy cat and make him happy. Now, the really neat thing about quantum mechanics, or one of the neat things, is that you can model these evolutions of quantum mechanical states with a very elegant subset of linear algebra. So here, this X gate is modeled as a 2x2 matrix. And so we can take our grumpy cat, remember 1 on the grumpy axis, 0 on the happy axis. We can multiply that by this X matrix. And now there's a little secret. When you multiply a vector times a matrix, when the vector is what's called a one-hot vector, which means it's just got a 1, 1 in it and the rest are zeros, you can identify what row that the 1 is in, and you pick out that corresponding column. So here, to multiply that vector by this matrix, we simply pick out the corresponding column, which is the first column, and that's the answer. And so our grumpy cat turned into a happy cat, 0 on the grumpy axis, 1 on the happy axis. And so we can model quantum mechanical calculations. Here, we're only talking about 2 dimensions. But we could model, if we had, 300 qubits, we could model 2 to the 300th power of dimensions, and we can get nature to do those fantastic, mind-blowing calculations for us on our behalf if we can set those quantum mechanical states up for it in the computer. So that's the promise and the challenge of quantum computing. So here's an example that's not classical. This one is quantum, where we have a happy cat or a grumpy cat. We're going to run him through a Hadamard gate. Now, Hadamard gates are great for putting cats into equal superpositions. So here we have a grumpy cat, run him through a Hadamard gate. Now he's going to be in an equal superposition of grumpy and happy. And so we can model that, the Hadamard gate, with this matrix. Got a grumpy cat, pick out the first column of the matrix, put them over here. The square root of 1/2. So this is the same thing as the square root of 1/2. It's just different notation. Square root of 1/2 grumpy. Square root of 1/2 happy. Equal superposition. Well, you're doing quite well. You've done 2 of the 3 axioms of quantum mechanics that I'm going to talk about today. The third one is this idea of measurement. So we have this, my cats are in this quantum state, but now let's say I want to observe my cat and find out, is my cat grumpy or happy? I can't know here his exact state in the quantum world. Nature doesn't allow us to look into the quantum world like that. But when I look at my cat, when I measure my cat will decide what state it's in and will collapse to one of 2 states. When I observe my cat, because the probability is the amplitude squared, when I observe my cat, what is the probability that he's going to be grumpy? Well, to take the square of the square root of 1/3, I would just simply eliminate that radical. There is a 1/3 probability of being grumpy and a 2/3 probability of being happy. And of course, we're not limited to one cat. I might have 2 cats. So here, if I have 2 cats, then I can represent them by a factor of 2 cats. It's a product state here, in which I would just have 2 grumpy cats, and I would take what's called the tensor product or Kronecker product of the 2, which is simply cross multiplying, and you end up with 4 basis states here. Grumpy, grumpy. It's basically a binary progression of basis states, in which, in this case, the first one is a 1, and which represents grumpy, grumpy. And I could do that with grumpy, happy. We'll do tensor products, and we find out that we have a 1 beside the grumpy, happy. And so if we put all this together, then we have maybe grumpy, grumpy, and then we run them through some quantum gates, and maybe they're in this position, and maybe some more quantum gates, and then we measure them. With a half probability, we would have this state. A 6th probability, we would have this state, and a 3rd probability, we would have this state. But with no probabilities is the possibility of having grumpy, grumpy. So they're in this quantum state. So another thing that Anamita talked about was this idea of quantum entanglement. Spooky actions at a distance is what Einstein called that. And the idea is that if you have 2 quantum particles or 2 cats, then you can entangle them, and quantumly they will be entangled to where when you measure one, you know what the other one's going to measure. Like, for example, let's say that we have 2 cats, and here we have a quantum circuit. These wires here represent our cats. And spoiler alert, when we get into quantum programming, quantum computing, these are going to be called qubits. But here we've got Alice the cat and Bob the cat. And Alice, we're going to run her through a Hadamard gate. Now she's going to be an equal superposition of grumpy and happy. We've covered that. We run a CNOT gate now. Now that's our first 2-qubit gate. That one actually spans 2 different cats here. It's got an X gate down here that is conditional upon the state of Alice. So whenever Alice is happy, it's going to flip Bob's state. And if Alice is not happy, if she's grumpy, it's not going to flip Bob's state. So that puts the quantum state into this equal superposition of grumpy, grumpy, or happy, happy, which is one of the Bell states. And so if they are in that state, and Alice gets into a spaceship and flies to Venus, and Bob gets into the spaceship and flies to Mars, if we observe Alice on Venus and she's happy, then we're 100% certain that Bob, when we observe him, will be happy. Conversely, let's say that we measure Bob on Mars, then we know that Alice, when we observe her, is going to be grumpy. And so here are the matrices that we can use to model the gates. This is a 2x2, but with this 2-qubit gate, it's a 4x4 matrix. If it were a 3-qubit gate, it would be a 8x8 matrix. And so this session has game in the title, and so I'm going to use a game to help you learn some more things about quantum computing before I turn you loose and actually have you make your own game. And so this game that I'm going to talk about is one that I developed called Qiskit blocks. And in the home page for this presentation, there's a link called Qiskit blocks. And if you go there, then there are some instructions for downloading the game and for running it and things like that. And so this happens to be one of the participants in the Code for Kids. And this kid, solved all the puzzles first and was probably one of the youngest participants. So there's some instructions on stalling and running. You can do that at your leisure. It's very much like Minecraft. As a matter of fact, there's an open source version of Minecraft called Minetest. And so if you're familiar with Minecraft, then you'll know how to play this game already. And so I'm going to go ahead and get in game here for you. So when you start up, then you can choose a world or make a new world. I'm just going to say play game. And when you go into the world, you're going to be in this room that will have all sorts of reference on different blocks. Like here, if you wanted to know more about the Hadamard gate that we just talked about, just right click. It tells you about the Hadamard gate. And then some other tools that you can have. And there's lots of things outside that you can play with. There's some cats and a quantum circuit guard and things like that. What I want to show you is actually in this TARDIS is a large portal hub. So I'm going to go into the TARDIS, and there's a portal hub in which we've got different levels built out. I'm going to jump into this first level, and we're going to take you step by step through a building and solving some quantum circuits. So when I get into here, it's a little bit like Portal, where you look around, you try to figure out, how am I going to get out that door to the next room? So I look around for clues. I see a chest. I see this door symbol over here. And I'm going to guess, based upon that, and also based upon this text up here up in the upper left, which Professor Q is over on the right is texting to me. She's telling me that I need to change the quantum state here to what's on the wall. And so I'll look in the chest, right click it, bring this down to the top wire here, or top line, so I can wield that block. And there's a nice little dotted outline here on this first one, so I know where to put this. I'm going to wield this X block and turn that 0 into a 1. And so the block turns gold. I can see that the probability, this liquid level, which represents probability, went from 100% probability of measuring 0 to 100% probability of measuring 1, which is the same thing that's on the wall here. So I've solved the puzzle, the door's open, and then I go to the next one. I'm going to go through these pretty quickly. I want to give you a good chance to play the game, or to do your own programming. But so here we have 1, 0. So note that the 1 is magenta. So that means that the most significant qubit is the bottom wire. So if I wanted to get into a 1, 0 state, then I would just put an X block on the bottom wire. So let's do that. We'll go there, and there we go. I'll go out the door. Where's the door? Let's see. Oh, there's one. And then here it's more of the same. I've got 3 wires, 0, 1, 1. I'll bet you there's an X block in here. Yep. There's going to be an X block over here. Bring it down, and then we'll put those X blocks here. 1, 1. So I got 0, 1, 1. Notice there's these funny looking things here. Those are called block spheres. They're representations, a very pixelated representation of a block sphere. I'm going to talk about that in a little bit here. But we'll go over to this ladder, climb up the ladder because the door is way behind here. And the next puzzle is one where we need to have a superposition of 0 and 1 with an equal likelihood of measuring 0 and 1. What kind of gate do you think is going to be in there? I'm guessing it's going to be a Hadamard gate, right? Because it works on qubits the same as it works on cats. So I'm going to wield a Hadamard gate. And notice that the liquid levels are the same, equal superposition, but also notice this block sphere. It went from being at the top to being here on the equator of the block sphere. So I want to take a little bit of a detour and talk about the block sphere. So there's another link in the presentation that you can get to this page. This page shows you an animated block sphere. So when you go to the page, it starts out here at the top. There are three, in a block sphere, there are three axes, an x-axis, a y-axis, and a z-axis. An x-gate rotates the quantum state on the block sphere by 180 degrees, or by, if you're used to radians, by pi radians. So we'll take this x, and now it went from 0 to 1. But what if we apply an h? Well, the h puts us in an equal superposition anywhere, by the way, on a block sphere where it's on the equator is an equal superposition. And that's symbolized by it's an equal distance between the 0 and the 1. So it's all equal superposition. It's just the phase. Remember Anamita talked about phase? The phase is different. Here we've got a 0 phase. Here we've got 180 degrees out of phase, or pi phase. Okay, so let's apply that to what to our Qiskit blocks. Here we're in that plus state. We've applied the Hadamard gate. We're in the plus state, in the equal superposition. Now we'll very quickly, instead of going to the plus state, we're going to go to the back of the block sphere, which is that minus state back here. So let's see how we can travel to the back of the block sphere. We'll go over to the chest to see what we have to work with. We have an X gate and a H gate. So let's see, which order should we put those on? Well, what if we put the X gate here, and we went from the top of the block sphere to the bottom, and then we put the H gate here, then what's happening here is we applied the X, which put us here, and then we applied the H, which put us back here. Now, what a Hadamard gate does, if I look straight down into this block sphere, a Hadamard gate rotates on that axis that's a bisection of the X and the Z axes. And so if I started out here, it's going to end up here at the bottom. If I started out here at the top, it's going to end up here on the plus. Right? And so that's how we got to the back of the block sphere. So in the next one, it's going to challenge us to do the same thing. Go to the minus state, but it's going to give us two different blocks. So the two different blocks are the H gate and the Z gate. So we could solve that by wielding an H gate. Whoops. I wielded it in the wrong place. We'll pick it back up again. I'm definitely playing Minecraft, right? Okay, so we got our H gate. Going to wield it here. That puts us at the front of the block sphere. And the Z gate, remember the Z? The Z is going to do a Z rotation around the Z axis, which is going to put us to the back of the block sphere. So here we'll apply the Z, and now we're at the back of the block sphere. Equal superposition, but notice that the phases are 180 degrees out of phase. And we have the minus there. So I'll just go through a couple more real quick here. I want to get to entanglement. Here's one. We want to turn the 0, 0, 0 into a equal superposition of 0, 0, 1 and 1, 0, 1. Well, taking that one at a time, if we want an equal superposition on the magenta wire, then we would just throw a Hadamard gate at it. So we'll do that. close enough here. And if we want a, let's see, the second wire, the yellow wire, is always going to be 0. It's already 0, so we don't have to change it. The cyan wire, we want it to always be a 1, and so we're going to throw an X block at it. And so now we can get through here. And then here, we want an equal superposition, an equal likelihood of all the states measuring. And so here, in Dirac notation, we're showing that the probability, remember the amplitude squared is the probability, so a fourth probability that will measure 0, 0, a fourth 0, 1, fourth 1, 0, fourth 1, 1. What do you think's in the chest? I'm guessing it's a Hadamard gate. If a Hadamard gate will put 1 qubit into superpositions, it'll put 2 qubits into 4 equal superpositions. So there we go there. And then going to the next room, we're going to do the same thing with 3 wires. We'll get the H gate out here, and we want that funny notation. That's basically a summation notation, saying we want an eighth, a probability of 1/8 of measuring all of the states. So an equal superposition where each one has a 1/8 probability. So we'll wield that block on that one. We see that each one has a 1/8 probability, equal superposition. And so now we can go to the next one. And now this will be the last one we do. And here, what it wants us to do, you should recognize this one. This is the Bell state. This is the one of the 4 Bell states. This is the one that most people think of when they think of Bell states. So it's an equal superposition of 0, 0. And if you'll recall, with the cats, we had a Hadamard gate and an X gate. And remember, we had a C-knot. We're going to use this tool to build a C-knot. So here, we'll yield the H gate. And then here, remember, a C-knot is made up of an X gate with a control wire. So here's the X gate. We're going to wield the control wire, left-clicking it. And now we have this state, equal superposition of 0, 0, 0, 1. Notice what happened in the block spheres. It's an undefined state. When you have entanglement, you can't, it's not a product of single qubits anymore. You can't define an entangled state in terms of individual qubits anymore. So now, with that introduction, what I'd like to do is go ahead and leave the game and then take you into the quantum experience. One little party trick I want to show you. I'm going to go back to the game real quick and show you one thing that is available that you can do. And that is, let's say that in our entangled circuit, we had this circuit. I can right-click this Q block, and I can see the quantum assembly language that is behind that circuit. And so I can take that quantum assembly language, and I can paste it into our IBM Quantum Experience Circuit Composer, and then have it show us that circuit. So I'm going to go ahead and do that. So I'll go to the IBM Quantum Experience. I'm going to go into the Circuit Composer, which is right here. And I'm going to say New Circuit. I'm going to go to the code over here. That code is the XML kind of looking thing. I'll go over here and delete this and paste what I got from in-game. And notice here that I have the Hadamard gate, the C-knot gate, and the 2 measurement gates. And so then I could run that on a real quantum computer or on a simulator or something like that. So first of all, I'm going to save the changes. I'm going to run it. I could select an available backend. So let's see what's available. I'm going to go to the dashboard and see over here are all the quantum computers that I have available. Notice how many jobs each one of them has in their queues. So here, our ENTs. I'm going to go ahead and pick on that one. It's a 5-qubit real quantum computer in the IBM cloud that you can use for free. And we're going to go to our quantum circuit here. I'm going to run it on our ENTs. And here we are. It's sent. It's sent to the queue. I can go down here now to the results. And I can see that it's in the queue and that it's running. And as I refresh it, I can see that it's no longer running, but that it just completed. When I refresh it here, it just completed. I'm going to click on it, and I can see, not only can I see some of the details about it, how long it took to complete, I can also see the original circuit diagram and also what's called the transpiled circuit. So the transpiled circuit is the gates that it transpiles it to in order to be able to run on our quantum hardware on that particular machine. And so then what are the results? Well, we had it measure it, by the way, by default 1,024 times. So it ran that circuit 1,024 times. And here's a histogram of the results. This many times, almost half, the result was 0, 0. This many times, this percent, it was 1, 1. And because current state of quantum computers aren't perfect, there's some noise and other kinds of things. A very small percent of the time, it actually read out an incorrect thing, because in a perfect quantum world, it would always be 0, 0 or 1, 1.
And this might be a good time to kind of tie back.
Yes.
What's actually happening, right? So we looked at the circuit, and Jim was able to run this on a quantum computer by calculating something on his classical device. So when he's drawing out these circuits and these gates, what this is doing is when he selects a simulator or the actual hardware, it goes into the device and it converts it to those microwave pulses. It goes through the device and it comes back and gives you this readout of 0s and 1s. So if we go back to the 3 steps in the basics, this is it all coming realized to you being able to use a quantum computer on the cloud.
Yes, thank you very much, Anami. That was great clarification. I appreciate that. So next thing I'd like to show you is the Qiskit site. It's qiskit.org, and so this is qiskit.org here. All sorts of resources you can look at. There's some YouTube. There's lots of YouTube videos on getting started, and some really some cutting edge research kinds of things, etc. There's also some nice materials for kids that my colleague Maddie Toad created. It's really cool stuff. And so we'll go back to the IBM Quantum Experience. Not only can you go into the Circuit Composer, but you can also go into notebooks. So when you're programming a quantum computer, you could use the circuit model, but that'll only take you so far as the complexity, the kinds of sophisticated and user-oriented applications you might want to create. At some point, you're going to want to write some procedural code to then programmatically create these circuits. And so if you go to Qiskit notebooks, then you can do that. So they're in resources, by the way, and there are some links here when you get to the lab. There's some great resources for being able to create your first quantum circuit and not only does it show you how to create a circuit, it's kind of a recap of what I just showed you. Also shows you how to get into the quantum experience, etc. But there's another one that that talks about how to create your first how to code your first quantum circuit. So here you can go through those instructions, and this will be useful in your lab when you do your lab, because you might find some of this code and some of the instructions pretty good as reference when you do your lab. So again, getting into the quantum experience, creating a new notebook. Here's some good boilerplate code that you might be able to leverage. You know, running that circuit, plotting a histogram, etc. And so when you get into the quantum notebook, the Qiskit notebooks, then one place that you're going to go is, when I say Qiskit notebooks, you're going to go to this page right here that has all sorts of links to tutorials, etc. I like to go here to start here, and then you can go down and get a nice introduction. And then here's a nice one on getting started with Qiskit, for example. You could go in, you could play with that notebook, and to play with the notebook, all you do is you highlight a cell or just click on a cell, and you can either hit Control Enter or Run, and it'll run that cell. And then here we could study, well, what's that doing? Well, we got some imports, where we're importing some Python code. We can go down here. We can create a quantum circuit with 3 qubits, 3 wires, and then it's explaining what we're going to create. And then here we're going to run this cell, which is in Qiskit using Python. That's how we put gates on wires. So here we're putting a Hadamard gate on the circuit. Here we're putting in a CX. As you can guess, it's a C0 gate, where the control wire is the 0 wire, the top wire, and the X gate is the 1 wire. And so then we can do things like visualize the circuit. We could run, and we could see our circuit, and then we could see some different visualizations. And so you can go play through that and play through the other resource that I just talked about. But I want to get you to the lab here. And that lab is expressed here in the homepage for our class. And I'm going to go down here, and here's a link to the quantum experience. And here's the challenge. Here's what I want you to do. Again, these 2 things are optional. I just showed you those. But if you have any trouble getting into the quantum experience or understanding some of the concepts about particularly coding a notebook, then you'll want to take this tutorial right here. But then as far as the project itself, here's the objectives. You're going to make a quantum 8-ball, and it'll be a command line kind of notebook-based application. And so you're going to go into the quantum experience circuit composer. The first thing is you're going to create a circuit to do that. You'll create a 3-wire circuit, and you're going to drag and drop the gates onto the circuit, go through these steps, and then every time you run that, it's going to come up with some answer between 0, 0, 0 and 1, 1, 1, representing the 8 states of your magic 8-ball. So then in this state, you're going to do the same kind of thing, only you're going to use Python, and you're going to do it in a quantum experience Jupyter notebook. And here are some of the objectives. You're going to create, using Qiskit and Python, you're going to create your circuit. And then you're going to have it print out a message unique to each measured state. For example, 0, 0 might be the quantum 8-ball says it's most likely. And here's some possible answers. If you'd like some hints, here's a partial solution. And so it's basically a solution to this problem in a Jupyter notebook that has, it's not completely solved, but it might give you some hints. And then here is a possible solution that, that if you want to refer to it, you might struggle with it for a while and then refer to it, or master it and never have to refer to it, or just compare it with your answer. And so get through that. And then if you have time, very newly introduced into Qiskit, into version 18, is the ability to do measurements like this, to sample from a quantum state without using a simulator. So you're using some methods of this state vector class. And so if you have time, use these two instructions or these two methods of that class to do the same thing. And then you might expand the circuit to 4 or 5 wires. And then what you might do, rather than have an equal probability of each state between 0, 0, 0 and 1, 1, 1, you might add some single and multi-qubit gates to your circuit and then see what effect it has on probabilities and results. And so if you have any questions, please ask. Anamita, what do you have to add to that before they get started?
I think this is it. I had one slide I wanted to share with everyone.
Okay, please do.
A place to get started. Let me share my screen with you. So I know a lot of you are going to go get started on the code now, and we will also be available for you as you guys go through the code and help you. But if you do leave us here and decide you want to work on this on your own time, Qiskit is the largest open source quantum computing project right now out in the world. You will be working and coding with Qiskit, so if you go to the GitHub, you'll be able to get up to date. There's some easy issues for you to work on, but it's a really good way to get involved with the community. We also have a lot of learning material for you. So we have an open source textbook where you can get started with the basics of quantum computing. We also have a YouTube channel where we post videos very regularly. There's content created for the researchers and scientists that are deep in the field, and also entry-level content. And we plan to launch a lot more on that channel in the coming months. And finally, after you guys get started today with your first part of code, or you get better at your quantum computing skills, in celebration of our 4-year anniversary of quantum computers on the cloud, we've issued a challenge to the quantum computing community. The challenge is 4 exercises that take you through different portions of quantum coding, algorithms, quantum circuitry, and it is a way for you to get more involved in the community as well as get started and put your skills to test. So I will let you look at this if you guys want to take any screenshots, whatever it may be. But for now, we're going to transfer back over to the GitHub and the code, and we are available for you to go through the questions, and then we'll go through the solutions at the end and maybe have a couple of you share your experience or the code that you've written.
So if you'd like to follow up, maybe Anamita, you could paste some of those links into the chat, and so that they can follow up afterwards with those. James, would you like me to share the screen or put you as presenter so that you can share where we're going to go next?
Yeah, sure. Go ahead. Yeah, that's fine.
Okay.
Okay, great. Yeah, so that's so please work on that, and then I'm sharing the screen, and so that as you have questions, go ahead and put them in the chat, and then I can share some things enough to where I'm not giving away things to the whole audience, but I'll be happy to interact with you like that. And Amita and I both will be on tap here. And thank you all.
I don't think we're seeing your screen, James.
Yeah, I'm gonna share it here.
Okay, great.
Yeah. There you go. And there, so there's the challenge. But then you also know where the site is, which is here, Qiskit in 2020. You can find this challenge.
I'll paste it.
I'll keep it up here. Yeah, okay, great. Thank you.
And if you guys have questions or get stuck, feel free to raise your hand or message one of us in the chat, and we're here for you. There's a question coming in about where individuals should post their code or if they need to send it anywhere. This hands-on experience, it's for you and it's a learning opportunity. So if you would like us to review the code, or if you want to send us your Jupyter notebook, we're more than happy to review it. But there's not a submission that's formal for this anywhere.
Now, if you'd like to submit code, you can take the Quantum Computing Challenge, and then when you submit your code, you can have the option of having it tweeted to the world that you solved the various levels of the challenge. So that's an option.
How's everyone doing? Are we logged into the quantum experience? And if you want to share maybe in the chat where you all are.
Unmuted you if you want to respond back without so that we don't that we get some interchange going if you're interested in that.
Answering this back, I cannot go to the scan and import invoices. I cannot upload.
He's saying he's got it working and quite proud.
I don't have the
Maybe if you'd like, Keith, you can do a demo of how your code looks.
Yeah, I think Naveen's actually having some issues, and we can't quite hear you, Naveen.
No, we haven't.
James, Mike's got a question about in the circuit composer, there's the density matrix representation. What is this?
So density matrix representation is a lot of times it's used for when you're trying to model noise in a quantum system. But normally, if there's no noise in the system, or you're using a simulator that doesn't have any noise, it's perfect, you know, then you only need that one dimension to be able to represent the quantum state. So it's more like, if you look at the circuit composer, you'll see one of the visualizations is called a state vector, and the state vector visualization. And so that state vector visualization has one bar for every basis state. So if you're dealing with 3 qubits, then you're going to have 8 bars, 8 basis states. But the density matrix has 8 times 8 basis states, or 8 times 8 bars arranged in a square. And so then you could model noisy systems. I don't use them other than, you know, with noise. So exercise like this, you're just fine with a state vector. One thing I forgot to mention is that there is a Qiskit textbook that would cover questions like that, like what a density matrix is and that kind of thing. It's a really approachable, nice textbook, and it's available in the, from the resources in the Quantum Composer, or in the IBM Q Experience. There's also a link to it in this presentation's homepage. I'm going to paste a link in the chat now.
taking another check with everyone out there. How's everyone doing? Does anyone feel comfortable walking us through their code and their experience? We can pass over this presentation to you.
Everybody shy? Hey, Mike, would you like to ask your question that you posed verbally?
Certainly. Am I unmuted right now?
Yes, you are.
Okay. Yeah, I must admit I was mostly playing with the circuits as opposed to writing the if-then statements about
Sure.
dates. What my question was, it sort of expanded upon what I said a second ago. For once we're out of simulations and once we're into sort of a real quantum computer, what we talked about having to reduce, do enough iterations to reduce noise to a reasonable level. What constitutes reasonable, and what are our techniques for finding that reasonable level?
So, Mike, it depends. So it depends on how many qubits you're doing and kind of what you're trying to get to. So if you have one qubit and you're trying to distinguish a 50-50 probability from like a 49-51 probability,
right,
you probably need a lot of iterations. And the difference between 50-50 and 49-51 could be blurry because of noise, or you don't have enough shots to look at. And then even so I think it's hard to answer that question because no one really knows. But if the answer is clearly 49-51 and not like 48-52, then that's another way to look at it. So I think it really depends on what you're trying to distinguish and how many qubits you're working with. Okay. Jim, I don't know if you have anything to add to that.
No, I think to add to that, I would have to talk to some of the researchers and get an answer. But that sounds good to me, Anamita. Does that help, Mike?
It's a start. Yeah.
Okay.
Yeah. No, I guess I'm sort of used to certain systems where you and obviously these are more classical systems, but where you sort of have to the error rate tends to sort of go down as the square root of how many observations you're taking, and I'm just sort of thinking of that in the back of my brain.
Yeah. So like Anamita said, your confidence level of sampling the underlying probability distribution. You can't peer into the quantum state.
Right.
So in order to know what the underlying state was, to try to get to the underlying state, as Anamita said, then you have to increase the shots, right? And so let's say that your question may be getting to the area of state termography, where let's say that you saw in the block sphere, right, where although a quantum state, like a two-level quantum state, can be represented in a two-dimensional vector space, you also have phase, right? So
right.
Actually kind of have three dimensions. Well, let's say that you wanted to know where on the block sphere a particular quantum state was. Well, you can't, nature won't let you observe it. But what you can do is you can measure it in three bases, right? In the X basis, Y basis, and the Z basis, right? So you could measure it like with respect to the equator. That's called if you measure it with respect to the equator, the computational basis, then you're going to get a distribution of of probabilities from 0 to 1. If you measure it, on another axis, then you'll get a probability distribution with respect to whether it's toward the plus state or the minus state. Remember the plus and minus states, right?
Right.
And those are the two most common ones, but you can also measure it in other bases to where, so anyway, you do that, and then through tomography, through the distributions that you're getting back, then you can, the more shots that you take in those three axes, then the more accurately you can describe or pinpoint where that battleship was on the surface of the block sphere, right? So that's the idea. I don't know. So that's what Anamita was getting at, right?
Yeah.
Yeah. So but anyway, past that, I'd have to hook you up with a researcher.
Fair enough.
Well, thank you, Mike, and thanks for participating in this lab. It's been a lot of fun.
Yeah, no, it was actually a good intro. I've been sort of looking at stuff, and I just have never actually dived in to do much. So it's a good motivator.
Cool. Well, hey, you've got another 27 minutes that you've earmarked for this. Maybe you could go to step 4 and knock this out.
So we're getting close to the last 10 minutes. I'm getting feedback from a handful of you that everyone's at different stages of their experience. Some have completed it, some are still struggling to get started. So we're here for the next 10 minutes to help answer any questions, so feel free to continue to reach out to us. And feel free to connect with us afterwards. You have the GitHub IDs, and feel free to ask questions in there or reach out to us on social media. I'll paste my email in here if you want to reach out to me personally, and I'll let James decide if he wants to do the same. And we are here for you as you begin and continue your quantum journey. So for the next 10 minutes, we're here, as well as moving forward.